Hi, this is Seyed from EDD Academy, and today I'm going to be covering Unit 6 on integration. Okay, so first we're going to look at a very classic problem, the area under a curve. Consider the following situation. You have the graph of y is equal to x squared, and wish to find the area under the curve from the point x is equal to 0 to x is equal to 1. How do you go about doing that? Okay, so this is x is equal to 0, and this is x is equal to 1. We want to find the area under this portion of the curve, alright? Now, this doesn't follow the shape of any regular shape we know, for example, a triangle or a rectangle, so there is no easy formula we can use. So how do we go about doing that? Okay, so let's take a step back. How about we start by trying to approximate the area under the curve? Alright, so how do you take the area of any complex shape? Alright, so let's say I just give you some random shape. Alright, how would you just go about finding the area of that? Well, you would break it down to the shapes of things you already know how to find the area of. For example, I give you something that looks like a mixture of like a half circle, a triangle, and a square. You would obviously break down to those shapes, and since you know the formula for those shapes, you would add up the areas and you would get the total area. Okay, so in this way, we're going to almost replicate that, but instead for an approximation. So draw some rectangles and fill in some of the area under the curve from x is equal to 0 to x is equal to 1. Now obviously rectangles won't fill up the area under a curve, right? Since it's curved and rectangles are, well, rectangles, right? But as you can see here, we'll get some level of accuracy in our approximation. It won't be very accurate, but at least we'll get a rough idea of what the area under the curve is going to look like. So adding up all the areas of these rectangles, like I said, will give us a rough estimate of the area under the curve. Now, there's a note to make here, all right? You could either overestimate or underestimate the area under these curves. For this entire for this entire lecture, I will be going with the assumption that we're going to be underestimating it at first. However, keep in mind all of this will work for a given rectangle in which the edges go over the curve instead of under. I just find it easier to illustrate it with rectangles that go underneath the curve. Okay, so assume that all of these rectangles have the same width delta x, which will make all of our calculations a lot easier. And then the area approximation then becomes, so the area will be equal to the sum of f of x sub I times delta x. Okay, so that sounds complicated at first, so let's break this down part by part. So delta x is the width of every single rectangle, and f of xi will be the ith subinterval of the range between 0 to 1. For example, x sub I will be the very first height of the, will be the very first beginning of the first rectangle, right? So let's just say that, let's say this line over here was x sub 1, alright? Now, clearly it isn't since the curve starts here, but let's just assume that it's this one, right? So then f of x sub 1, sorry, will give us this height right over here, okay? And since height times base is equal to the area of a rectangle, then we'll have the area of this rectangle. Then f of x sub 2, that'll give us this point here, and f of x sub 2 will be this height over here times delta x, since they all have the same height, and that'll be this. Okay, and then we'll just continue going on, and we'll just sum up all of these rectangles. Essentially, you can just replace this f of x sub I times delta x by a general let's say a that would represent the area of rectangle. So it'd just be sum of I is equal to 1 to n of a sub I. Now this delta x term, just for future reference, is equal to the uh, end of the interval minus the beginning of the interval, all of that divided by how many rectangles you want to be divided into. Or in other words, b minus a over n. That'll become relevant later. Okay, so now to get an even better estimate, what you would probably do is break down into even more rectangles, just break it up even more. This is a little bit of a rough drawing, but I'm trying to illustrate that by adding in more rectangles, you're going to increase your accuracy because you're going to be able to fill up more of those spaces. Alright, or vice versa, if you have an overestimate of rectangles, by making them smaller and thinner, you'll be able to go under the curve a little bit more and decrease your overestimate. Okay, so now let's use some of that calculus stuff we know. By taking a limit as n, the number of rectangles we want to have goes to infinity, alright? Since delta x is equal to the last subinterval minus the first, over n, the width of each rectangle will also go to 0, right? So we'll end up with almost as if we're adding up lines. And since adding up lines will give us an area, right? We get this formula right here, which is called a Riemann sum. Essentially, you're adding infinitely thin rectangles that line up at every single point together to get an area. All right, this is called a Riemann sum. And there are two forms of a Riemann sum, a left hand and a right hand Riemann sum. A left hand one is this right here, where at each interval you use the smaller x value, right? And you get an underestimate, right? And for a right-handed one, you use an overestimate, right? So imagine instead of using this point as the height, I used this point as the height for this rectangle. Oh, sorry, this height as for the height for this rectangle. Now, as the limit as n approaches infinity, those two are equivalent. The left and right hand approach each other since they both become the area under the curve. Now, this has a special name for it. We define the definite integral from point A to B, A being x is equal to 0, and b being x is equal to 1, as the limit of the Riemann sum as n approaches infinity. And it's indicated by that fancy symbol right over here, the integral sign. So what we indicate this as the integral from a to b of f of x dx. This dx is the differential that you have become accustomed to. And this differential is there because it's an infinitely small width of the rectangle, and f of x just becomes, since it becomes a continuous variable at every single point, I then increases by some minuscule amount, making it a continuous variable.